All right, welcome back. MEC 1330. We're going through Chapter 6 now. We skipped over Chapter 5. We're heading into Chapter 6 here, and it's hydraulic directional control, or we call them directional control valves, or DCVs, when we reference them on the 870. Okay? So we're going to get into kind of the meat and potatoes and what's really going on the inside of them and how we can control things. Okay? So remember the three segments for fluid power. We have our power input, right, which is our prime mover and our pump. We have our control valves, okay, controlling the direction, pressure, and flow. Okay, so that's what we're going to get into here. And then eventually we're going to get into our output. We'd already talked about cylinders and things like that, but we'll talk about motors a little later on. All right, but more commonly known for us, DCV, directional control valves. Okay, so generally we tie those to a solenoid. Okay, so that we can use electronic switching to open and close the valves to control which way the fluid is flowing through, whether it's hydraulics or pneumatics. Okay, we have a PCV, a pressure control valve, so we can control the pressure in the line. And then we have a FCV, a flow control valve, where we actually meter the flow. We can meter in or meter out, all right, but rule of thumb is metering out. All right, so first valve we use to control things called a check valve. Check valve is very similar to what we do in electrical with a diode. Okay, remember a diode allows current to flow only in one direction. A check valve does the same thing. We're going to allow flow in one direction, and it opposes flow in the other direction, or blocks flow in the other direction. All right, so you can kind of see the schematic symbol for it down on the bottom right-hand side. You're going to need to know that on the test. All right, you can see that it's kind of a ball and spring return type scenario where if we look at the middle bottom picture, right, if we have flow against the ball, all right, it's able to push the ball against the spring and allow fluid around it. But if flow was to go from right to left, all right, flow would come in through the spring and it wouldn't be able to push the ball. The ball would be stuck where the valve seat is there and not allow flow in the other direction. So that's really, if you take a look at this, what's going on the inside of it. And literally, if you look at the schematic symbol, that's telling you which direction it's allowing flow versus which direction it's not allowing flow. If the ball can freely move open, all right, well, that's the direction we're allowing flow in. Okay? So generally, we run check valves in parallel with other components, so we can allow fluid to pass through the component, or when it chooses path of least resistance, we're able to bypass the component the other way, all right, in going through the check valve, because the check valve will have least resistance, allowing it to flow. Okay? So on the diagram on the left, flow can't go through the check, so it has to go through the component. There's where we're forcing it. And we do this a little bit when we're metering, so we can control whether we're metering in or metering out or doing that sort of thing. Okay, on the right-hand side, we have flow can go through the check, and it bypasses the component. All right, so that check valve is where we're really using it to force the flow through the component. Okay. Now, different ways. Okay, not just pressure on. We can also do a pilot to open, or it's kind of like we call a remote type open. Okay, so we have a pilot to open check valve. If you look at the schematic down below, that is what it's going to look like. That little dashed line there going into the check valve is our pilot line. Okay, it's a separate hydraulic line. It's used for control purposes only. So we send the pressure to the component, and then the component reacts to that change in pressure. All right, so it acts similar to a standard check valve when there's no pressure applied, and it allows flow in one direction. But when sufficient pressure is applied, flow is allowed in both directions. Okay, so we can use that pilot line to help control that if we need to. Okay, we can do pilot to close as well. Okay, so if we want to block flow in both directions, we can use a pilot to close. Notice it matters where the dashed line is. I'm going to step back a slide. On the first one here, the dashed line is pointing towards the ball, so it allows the ball to open up. Okay? On the second slide here with the pilot to close, the dashed line, okay, is forcing the ball, okay, into the valve seat and forcing it closed. Okay, so we're going to use the pilot line to make sure that we cannot actually use flow in that direction, if that makes sense. Okay, so the pilot line is going to make it so we can't use in both directions if we don't want to. Okay, but the pressure from the pilot line would control that. The most common one is pilot to open. Okay, and pilot to close is the least commonly used one when we talk about this. Okay, next up we're going to talk about shuttle valves. Shuttle valves allow two alternate flow sources to become connected into one branch. Okay, the one with the highest pressure is going to dominate and push the ball the other way. So you need to know the schematic symbol down below. It looks kind of like two check valves, back to back, if we take a look at that. But looking at the diagram, right, if the pressure is greater coming from the left-hand side, it's going to force the ball to the right and sit in the valve seat. So what do we have coming from that tank or that side, okay, is going to be pushed through and allowed to evacuate. Or if the pressure is greater from P2 on the right-hand side, it's going to push the ball to the left, okay, and allow whatever fluid's coming from the P2 side, all right, out and through port A. And on the right-hand side, there's a cutaway so that you can see, exactly what that looks like and how that ball is able to transfer, back and forth based on which pressure is dominant and how it sits in the ball seat and doesn't allow it to flow. Okay. All right. Next, we get up into two-way directional control valves. Two ways. Okay. It's a cylindrical spool, slides back and forth. Okay. And it's shown inside the valve body to either connect or block the flow between ports. That's important because if we're connecting the flow, okay, we're going to call that normally closed. If we're blocking the flow, we're going to call it normally open. Okay, so those are really the two types that we're going to talk about. Two position, normally open. Two position, normally closed. The one that I have drawn, or the one that's shown at the bottom of the screen here, okay, we're going to call that normally closed. Look between A and P. That's normally closed because right now there is no flow between P and A. Okay? So the pilot to the actuator piece. Okay? That's why it's closed. On the right of that, we see the arrow going up. That's when it's actuated. Okay? So this is a normally closed, or a two-position, okay, two-way, normally closed directional control valve. So what happens here is it's normally closed, meaning we're not allowing flow. We push that button on the right-hand side. That opens it up for flow, okay? So then we can actually get stuff to flow. When we let go of the push button, we have a spring return on the right. It automatically returns. Okay, so this one is what we call normally closed. So if you want to think about normally closed means we're not allowing flow. Normally open means we are starting out allowing flow, right? The hole is open sort of thing. Okay? So if we talk and break these down, okay, a normal state for this, okay, this is a two-directional control. This is the normally closed position. Okay, so schematically, it's what's shown on the left-hand side. All right, A and P are not connected. And then on the inside of the cylinder is what we have shown on the right-hand side, or inside of the valve body. I'm sorry, not a cylinder. Inside of the valve body. Okay, so we have the inlet port, that's P. Okay, and then port A is off generally to like our actuation or things like that. Okay, so when it is normally closed, nothing is allowed to flow until we push the button on the right hand side, and then fluid is allowed to flow from the inlet port out through port A, or the actuation port. Okay, so it's kind of what I talked about on the previous page, but now you get a picture of it. So we can buy valves in both ways. They can start out as normally closed, okay, and then we actuate them to open them, or we can buy them the other way, where they're normally open and we actuate to close them. Okay, so it just kind of depends on, what we're looking for in our system there. So this one is a normally closed two position, okay, two-way. Now two position, I'm going to step back a slide. The blocks are the positions. So see how A and P have a block, and then the one next to the button has a block. Those are the number of ways, okay? And that'll make the number of blocks is the number of ways, okay? Or positions, and then, sorry. Positions is the number of blocks. Ways are going to be like the number of tick mark, okay? So this is two-position, two-way directional control valve, okay? It'll make sense to you when we see the third one. Okay, let's look at this one now. This is a two-position, two-way, normally open, okay? Sorry for a second there. I just misspoke. I was getting ahead of myself. This is the actuated state of the previous one. So I'm going to step back a slide, okay? We look at slide 9 here, okay? This is the normal state of this two-way directional control valve that is two-way, normally closed, okay? So if we buy it off the shelf, this is what's happening. Fluid's not allowed to flow. Then we press the button. I talked about it. I forgot I was on the next slide here. Didn't want to get ahead of myself. This is the actuated state. So when I'm pressing the button, okay, like what I talked about a minute ago, we're coming through P, all right, our inlet port out to our actuation piece, okay? Now, next, let's move on to the other one. We have a two-way directional control valve, okay? This one's when it's normally open, okay? So normally open, the symbol is flowing there. So in this case, if we buy it off the shelf and we put it right in our system, we're going to have fluid automatically flowing from our inlet port, okay, to our actuation port. Then when we actuate this one and press the button, we close it, okay? So this is a two-way directional control valve that is normally open, okay? Actuate it to close it. So it's the exact opposite. All right, so here's how we can kind of use an example of our two-way directional control valves. So on this diagram, on the left-hand side, we're draining a tank. On the right-hand side, we're filling a tank. So this is an example of where we'd use it. So in the picture on the left-hand side, okay, both are that valve on the right where it's draining through. You can see the little green arrows where it's draining through, okay? That's if we actuate it, right? That is a normally closed valve. That is a two-position, two-way, normally closed control valve, okay, or directional control valve. It's normally closed, right, because we don't want the water to automatically flow out of the tank the second we start filling it. So the only way for us to drain that tank is to push the button. When we push the button, it drains the tank out of the vessel and back into our return tank system. Okay, on the right-hand side, we're filling the tank. That is still a two-way, normally closed DCV, right? Directional control valve. When we're filling the tank, we're pushing the button right now to fill the tank because we don't want the tank to autofill or auto-drain in this particular scenario here. Okay, so we're pulling from our reservoir tank. We're using our hydraulic pump, right? How do we know it's a hydraulic pump? Because it's got the black triangle sitting in there, all right? And we're going through the actuated side of the valve with the green arrows, and we're filling the tank. So remember, the actuation side is next to the push button in this case, or if it's a manual lever or those sort of things. Okay? The opposite that is where the actual original state is. So in this particular scenario, both of these valves are two-way, normally closed directional control valves. Okay, normally closed, meaning we're not initially allowing the fluid to flow through. Okay. Now another way, we have a two-way directional control valve. If we have this, if you look, I need you to know that schematic symbol in the bottom right-hand side. Okay, it looks like kind of a bow tie sort of scenario. But this is common. Some of you guys might put this on the end of your garden hose if you're outside watering something, all right? Little shut-off valve. We use these type of valves on our pneumatic system in class as well, okay? But these are ball valves, okay? It has a ball with a hole in it and turns the handle so that the hole aligns with the flow. So on the upper right-hand side, you can see where the hole is, all right? So when it's parallel with the line, it allows fluid to flow through it. If we turn the ball perpendicular with the line, it seals off and doesn't allow flow through it, okay? Now, three-way directional control valves, okay? Looking at the schematic symbol on the bottom left-hand side, you need to know that, okay? So make sure that you draw that, have here in your notes, and you're going to be tested on knowing the schematic symbols for each one of these. Okay, this is a three-way, two-position valve. Okay, normally closed. How do we know it's normally closed now that there's a three-way? Now, how do we determine the number of ways, first of all? Well, we can look at the letters, right? Now there's an A, a P, and a T. Okay, so that's going to indicate the number of ways. Those are the three ways. And how do we know that it's closed? Because we're going from the actuator back to the tank. If we were going from the pilot inlet to the actuator, we would then it would be normally open because flow would be going right away. But since the initial state is going from actuator to tank, we call this normally closed. Okay, so this is a three-way, two-position, right, because there's two blocks. It's a push button, and then the squiggly on the left-hand side is a spring return. Okay, so if we look at the normal state here on the left-hand side, we can see it's going from actuator to tank. Then when we actuate it on the right-hand side, we're filling it, right, or if we're filling a tank, or we're allowing flow from the pilot inlet to the actual actuator. Okay, so this is a three-way DCV. Okay, we're going to make sure that we know all these. Now this is just like the last one, only we're going to start out with normally open. This is still a three-way, right? Because if we look at the letters A, T, and P, so there's three of them, it's still a two-position, right? And it's a spring return push button. So we know that this one is normally open in the symbol because we're going from the pilot inlet to the actuator. It means we're automatically actuating there. Okay, so it's the exact opposite of the previous slide when we looked at it. Okay, so normal position, we're allowing from our pilot inlet to our actuator. Actuated position, we're putting a force on that push button on the left hand or on the right hand side diagram, and we're returning stuff back to the tank. All right, and it's going to do that as long as we push on the button, and then it'll spring return. Okay, you guys are going to do some labs on this in class and hook these things up. Now, this is a three-way directional control valve still. It's set for, now it's called a pressure relief valve. Okay, and we're adding that onto the three-way valve. Okay, so if we look on the schematic on the right, if we want to extend and retract a cylinder, we have a three-way DCV, and then we also have a PRV, the pressure relief valve. You need to know that symbol. Now, here's the point of that, right? If we're not extending or retracting the cylinder, right, we still want the pump going because we want to be able to instantly extend or retract the cylinder as need be when called upon. But if we don't have the pump going and there's not enough pressure on the line, that won't happen when we want it to. So we keep the pump going. So what will happen is, even though we are using a normally closed DCV, the pressure will build up on the line and sit there, and it'll be ready. But if the pressure gets too much, we use a pressure relief valve, all right, that kicks that back into the tank. So that helps maintain a constant pressure in the line for us without building up pressure and ruining the line, right? Because our directional control valve is closed, but we need to give it some relief, but we want to make sure that we maintain that constant pressure on the line. So very, very important, very common for us to use pressure relief valves on these kind of closed loop systems here, okay? We also have a detonant, okay? That's a mechanism that holds the valve in the position which you shift it, okay? So if we look now at the schematic symbols in the middle, those are now three-way, three-position. Okay, now there's three blocks on these control valve schematics, right? Three-way, three-position. On the right-hand side, you'll see it's the manual lever that's on these. So there's three positions. Okay, the middle position is everybody's closed. Okay, and it holds it there. Now we can move the manual the manual lever to the left. All right, and we might be going from A to T, or we move the manual lever all the way to the right. Okay, we might be going P to A. Okay, so we can do that. This is exactly what you guys are going to do in the lab, and it's going to make sense. So for us, this is how we can have a middle position where it's not doing anything, or we're able to extend a cylinder, or retract a cylinder. But we don't have to hold it in that position. So if we put the cylinder to the right, it's going to hold it in that position sort of scenario. Okay? So, very important that we understand what a deton is. And the deton itself, okay, is represented, it's the saw-looking thing on the left-hand side of the three-way, three-position control valve. Okay? It's labeled here on the picture for you. So when you see that or on the test, and I point specifically to that piece, you need to tell me that that's the deton on the schematic side of things. Okay. We also have what we call a diverter. Okay, so very important here. Okay, it has one pressure inlet and two outlets. Okay, so in one position, pump flow is sent A to B is blocked. In the other position, flow is sent from B to A is blocked. All right, so it just kind of depends on it, which one we want to divert everything to. And you can clearly see kind of how we can divert it. All right, so we've got two different systems here. We want to divert everything to, system A instead of system B. So we can use a diverter and send everything over to one side and not the other. Okay. Now, this is a four-way directional control valve. Okay, it's the most common because we use them for our double-acting cylinders, which are most of what we use in the lab today. Okay. Notice this is a four-way, two-position directional control valve. Four ways because you can see A, B, P, and T. That's our number of ways. Okay, the positions are the two blocks. We can see that it's spring return and it's push button activated just by looking at that schematic symbol. So make sure you know that schematic symbol. Okay, so in its normal position, you can see that it's going from A to T and P to B. So when we install it, that's how everything's going to flow. When we push the button, it makes it go P to A and B to T. Okay, we use this for double-acting cylinders. So we have this pneumatically on our entire system as well, but you'll have these on your hydraulics labs in class as well. Okay, now we're going to get into different types of centers. Okay, so we have a four-way, three-position. Okay, it uses with these. Okay, they have a third position called the center. Okay, so it's a four-way because it's A, B, P, and T. Okay, and it's three positions. Okay, you can tell because of the three blocks. Okay, it has a manual lever, it has a detent, and it has a spring return as well. Okay, so the different types of centers that we're going to talk about are the closed center, the tandem center, the float center, and the open and regenerative center. Okay, so schematically on the left-hand side, you will see the closed center, and that's the center position, okay, on the four-way directional control valve. It's the middle block that you're looking at. Look that it is completely closed. There is nothing flowing from one direction to the other. Okay, so that's how it is before we actuate it. On the right-hand side, we have a tandem center. Okay, so you can see that that's diverting flow back to the tank so that it just keeps sitting there until it's called upon for us to either extend or retract the cylinder. Okay, so verbally, the closed center, the pump line's blocked, so flow goes over the pressure relief valve. Okay, when this happens, the pressure in the system's at a maximum. It goes unused. The outlet lines are blocked, so the cylinder's held in place. So a closed center could be used to control a motor. Okay, so if we step back and take a look, all right, that's a closed center. Okay, the tandem center, right, pump flow is allowed back to flow through the tank. I already mentioned that previously. Through the DCV when it's in center. That keeps low pressure in the line. Okay, and this position is said to be unloaded and the power consumption is reduced. So I'm going to step back a slide just so that you see, all right, it's going back into the tank and that's what's going on. Okay, other centers here, right, we have the float center, okay, the float center, and then the open center. The open center is pretty obvious what's going on. The float, let's talk about it. Okay, the pressure port's blocked and the outlets connect to the tank, forcing the flow over the pressure relief valve value. Sorry about that. Since both outlets are connected to the tank, the motor will float or spin freely in that position. All right, we're not particularly controlling it that second. It's allowed to spin freely. The open center, okay, the pressure port and the outlets are connected to the tank. All right, flow is going to be the path of least resistance. So pump flow goes back to the tank. The cylinder is going to float when the valve is in the center position. Okay, so what does it mean when the cylinder is going to float? That means it's going to neither extend or retract. It's going to kind of like balance and stay in neutral when we're looking at that. Okay. Lastly, let's talk about the regenerative center. Okay, that's waste is fed back to supplement the input power. So we're using what we're taking out of it to put it back in. So we don't have to use as much power, right? Because normally we're going to return everything to the tank and then suck it back out of the tank with a pump and that sort of thing. So what we're doing is we're using our output, all right, whether we're extending or retracting, we're using the output port and feeding it back to the input port. You know, like I said, whether we're extending or whether we are retracting, okay? So the pressure port's connected to both outlets and the tank port is blocked. So when that happens, okay, the valve shifts to the center, the pump pressure is applied to both sides of the piston, all right, and that's going to help increase speed. So that's one of the main reasons we do that, okay? So for us, it's used in the circuits where the cylinder has to be moved into position quickly, so we don't waste time pulling a bunch of extra fluid from the tank and returning a bunch of fluid to the tank. Okay, so that's the whole purpose of the regenerative center. Okay, so a couple calculations, not too many in this chapter. All right, it's not loaded like chapter 2 and 3. All right, but we want to talk about our regenerative velocity, or our V regen. Okay, it's 231 times Q plus QR. All right, so remember Q is flow rate, and then we have our regenerative flow. So there's two flows now, right? The flow that we're kicking into it to extend or retract it, right? And then there's the QR, the flow that's coming out and aiding the system. That's why it's adding. So the equation on the left is for our imperial units. The equation on the right is for metric units. You should recognize the 231, right? Cubic inches for water. You should recognize 1,000, right, tied to liters for flow there. So if we talk about flow from the rod end, okay, right, flow's coming out of the rod end to help us extend it, all right? So we're coming out of the rod end and going into the blind end. So our QR, our flow from the rod end, okay, is going to be our regenerative velocity times our difference in our area divided by 231 in imperial units, or it's going to be 1,000 times our V regen minus the difference in area if we are doing it in metric form, okay? Then we can substitute everything in, and we can calculate it this way as well, okay? So let's do an example. We have a cylinder with a bore diameter of 3 inches and a rod diameter of 1.15 inches is to be used in a system with a 15 gallon per minute pump. What are the extension speeds when regenerating and when not regenerating? Okay, so remember, regenerating, we're kicking it back to the system when we do that. So as we've been doing over and over and over, find the area of the piston, find the area of the rod using pi d squared over 4. Calculate the normal extension speed. So if we're not regenerating, right, just normal velocity it is for us to extend the cylinder based on the flow rate. Okay, the flow rate given to us is 15 gallons per minute. So it's just going to be 231 times 15 divided by 7.07. Okay, so our extension velocity is 490 inches per minute. So the regenerative extension speed now, we're going to substitute into the equation we did on the previous slide, 231 times Q divided by the area of the rod. Okay, so it's going to be 231 times 15 divided by 1.039. So our regenerative velocity is 3,334 inches per minute. Okay, so those are the expansion speeds when we're just normally going versus if we are using our regenerative system piece there. Okay, so then force, okay, is pressure times area. So we can use our extension force if we are normal, okay, using our normal one versus our regenerative extension force, okay? So really you can look at the difference there. The difference there is really just whether we're using the piston side or the rod side. It's just the difference in the area, okay? All right, let's do one metrically. A cylinder with a bore diameter of 60 millimeters, rod diameter of 20 millimeters. This will be used in a system with a 30 liter per minute pump. What are the extension speeds when regenerating and when not regenerating? Okay, same as normal. We've got to take that 60 millimeters, turn it to meters, move the decimal 3 places to 0.060. Likewise with the 20 millimeters, it's got to become meters, so 0.020 meters. Calculate both areas so that we are in the correct units, and then substitute into our extension velocity and our regenerative velocity. Okay, so we have all the data. You guys should be able to substitute in there. And then, once again, calculate the forces. Use one of the forces using the area of the piston, the other force using the area of the rod. All right, we're able to go through this. So it's just like the last example, okay, only we're doing everything in metric instead of imperial. All right, so just to review the different types of centers we talked about, we had a closed. Okay, the effect on the actuator is it holds the position. Where does the pump flow go? It goes back through the pressure relief valve back to the tank. If we had the tandem center, okay, it holds the position, and then it goes back through the directional control valve back to the tank. If we have the float, okay, through the pressure relief valve back to the tank. If we have an open center, okay, the actuator floats, and where the pump flow goes back through the directional control valve to the tank. If we had regenerative, all right, extends quickly with less force capability, right? That's the effect on the actuator. We're speeding up that extension. And the pump flow, this is the only one that goes back to the cylinder, right? We're kind of recycling and reusing to give it an oomph when we do that one. Okay? You need to know all these symbols for your test, all right? So the first one is a manual lever. Now, on the test, you don't have to write everything out for me each time. We can clearly see that this is a 4-way, 2-position directional control valve that's spring return with a manual lever. I'm just talking about the first one. But all these valves are all 4-way, 2-position valves. They all have a spring return. You don't have to write that piece on the test. I'm looking for more that you understand the manual lever symbol, the push button symbol, the foot pedal symbol, the cam, okay, so a cam, right, shift when depressed by a mechanical component of a machine, okay, so computer-aided machining on that piece. The next one with the little black triangle, that lets us know that that is a hydraulic pilot operated, okay, it's a hydraulic. If that triangle was open, it would be pneumatic. So that, just with the little triangle on there and the dashed line going in, that tells us that it's pilot operated. Okay, the second to last one, the little box with the line at a diagonal, that's a solenoid. Okay, remember the solenoid is a coil of wire that we put a current through. It creates a magnetic field and opens and closes the plunger. Those are very common, right, on the 870 trainer that we have and that we work with. Okay, and then the one at the very bottom, it's a pilot operated solenoid. Okay, so you need to know that's the part I'm looking for, is really what's located on the right hand side of all of these directional controls here. I'm looking for you to understand what the actuating mechanism is on the test. Okay, so if we look at just a main valve position and how we are going to extend and retract a cylinder. Okay, you're going to hook all the hoses up in the lab and do this pneumatically. Okay, but if we take a look, we're going to move left to right. So right now we have what? A closed center, right? Nothing's flowing in either direction, and our cylinder is neither extending or retracting. Okay, then if we shift it to the left, okay, we're using a what to shift that? A solenoid, right? That's the little box with the diagonal in it on the left hand side. So this would be, how we're doing it on our 870 trainer, only it's pneumatic instead of hydraulic. But we're going to use a solenoid, okay, and then we're going to get what? From our pilot inlet valve, right? That's what's pulling from our tank. Okay, it's going through A out to the actuator and going through, and we are extending the cylinder. Okay, notice the fluid's exhausting from the rod end back to port B and back to the tank. Okay, so this is not regenerative, right? We're going to pull stuff from the tank to extend the cylinder and fill the blind end of the cylinder and evacuate everything out of the rod end of the cylinder and replace it back to the tank. So that's if we are shifted left using a solenoid, we're extending the cylinder. All the way on the right-hand side, okay, if we're using a solenoid to retract the cylinder, okay, it's going to shift it all the way to the right, okay, and now our pilot inlet valve pulling from the tank, okay, is going from P to B, and it's going in the rod end of the cylinder and forcing the piston back into the left while evacuating out of the blind end of the cylinder through port A back to the tank. Okay, so there's how we're kind of sloshing fluid, back and forth between each side of the cylinder in order to extend and retract the cylinder. So there's how we're using directional control, all right, to extend and retract a cylinder, all right, using a normally closed center. All right, so if I look at this valve, it's solenoid operated. Okay, the main valve, if we're looking at it, solenoid operated. Okay, normally closed center. All right, it's a 4-way, 3-position. Okay, the positions are center, left, and right. Okay, and it's held in place or controlled with the solenoid. Okay, so if we take a look, I want you to look at the actuation piece on the return on these. So if we look at each symbol here, what's written on the right hand side is what I would expect you to write on the test. Okay, so if I'm asking for the positioning or what holds it in the position or how it gets back to its position. Okay, so the top one is spring return, right? It's the little squiggly looking like heartbeat thing on the left hand side of the control valve. We already talked about a detonant, okay, and then we have a spring centered one. Notice the spring is sitting where the manual lever is. Okay, so we have a spring on the left hand side, and then there's a small spring on the right hand side where the manual lever is. That's how we know it's a spring in the center. All right, so it pops it back to the center. Okay, and then on the bottom one we have a 3-position detonant. That will actually hold it in the left position, the middle position, or the right position. Okay, and that's because we have a 4-way, 3-position directional control valve there. Okay, so a basic circuit here. Okay, if we wanted to draw this out. We did this in electrical, right? We would draw out series and parallel circuits and how everything kind of went in flow and current flow and that sort of thing, whether we had something in series or we had parallel branch currents and that sort of thing. But we had to know all the parts and pieces. So what I want you to get off of this part and piece is understanding what different things are on the actual schematic piece here, okay? I want you to clearly see that what a jump line is it's not a physical line in the field. The jump is only on the schematic so that you know that those two lines do not connect there on the drawing. All right? It's not physically out in the field and there's something that's special. All right? Because it doesn't look like this when you wire it up in the field either. Okay? But in this case, the jump line shows that it's crossing over that main line in the middle. It means that they are not connected. Okay, if we want a junction, okay, where the lines are actually connected, look at all the black dots on this diagram. Anywhere there's a black dot, remember we called that a node in electrical class. Okay, that's a junction. Those lines do physically connect there, okay, most likely through a T or something along those lines. Okay, we can see where the main pressure line is, okay. and it's where it's going through from the pump. Okay, we can see where the tank line goes. Okay, that one's clearly labeled. All right, and you can see the tank line, right? Everybody ends up at the tank. The tank is in the upper right-hand corner. It's the little, it looks kind of like the reverse of a ground sort of thing, or a little like hook lift type system, okay? We should all know what cylinders look like by now. We should all be able to tell where the center of this valve lies, okay? So, how do we mount these things? Okay, a couple different ways. We do inline mounting. So that means that they're fitted, all right? And I can show you in this class, right? Our pneumatic lines are inline mounted, all right? So this is like, our ball valve, right? Remember the flow here will allow flow parallel through the line, and if we turn the valve perpendicular, it cuts it off, okay? Disadvantage for these guys is you have to cut into the line and re-screw these ones in, all right? Because they are threaded. Okay, so if something goes bad on here, it's not a fun way to replace these things. Okay, so we use that in our pneumatic lines. You do have these on your main manifold on your hydraulic trainer. You guys will be using shortly. Okay, last in the bottom here we have subplate mountings. Okay, and that's how we're mounted on the 870 trainer. So we can go over and physically look at those. Okay, so that's how we mount them to these subplates. We have a manifold that sits on them, and then that manifold, okay, attaches to our DCVs, and then on the outside of our DCVs we have our solenoids or things like that. Okay, it's easier to replace. We have a manifold system than something that's in line. Okay, but it just kind of depends on the application, what we're doing. All right, most of the inline stuff, it's because we're running on pipes or those sort of things, versus actually mounting to the equipment when we use the subplate mounting. Okay. If we're looking at DCVs, you got to understand different things when you're looking to purchase them, if you ever are. Okay, any ratings between 3,000 feet and 5,000 psi, those are generally typical ratings. Okay, and 500 psi and 1,000 psi, they're typical for tank. Okay, flow ratings. Okay, so those are determined by the size of the valve. Okay, typical flow ratings are generally 10 gallons per minute up to 100 or up to 250 gallons per minute. Okay. All right, so let's take a look, do a couple calculations here. This will be the last one that kind of helps you on your homework here. What will the pressure drop be across the valve at a particular flow rate? Okay, so we're going to do an example here where we have to pull everything off the graph here. Okay, so first before I go through the example, we'll understand the graph. We are looking at a tandem center, all right, which means what? The cylinder's neither retracting or extending in that case. We're using this DCV here. It's a 4-way, 3-position valve. Okay, we're using hydraulic oil. Okay, on the left-hand side of the graph, we got the pressure drop. On the bottom of the graph, we have the flow. And on the right-hand side, it's telling us if we are going from P to T, where its status is, if we were just to install it, okay, it's going from pilot back to the tank, or if we're going from A to T or B to T, anytime we're returning from one of the actuators to the tank, that's going to be our dash line. And then our solid line is anytime that we are going from our pilot to either one of our actuators, A or B, when we do this. Okay, so just understanding what's going on here. So a cylinder, we have a bore diameter of 2.75 inches, and we have a rod diameter of 1.25 inches. We're going to use it in a system with a 12 gallon per minute pump. We want to be able to use the graph to determine the pressure drops when the cylinder is retracting, meaning we are going from P to B and A to T. Okay, so that's the retracting piece, P to B and A to T. Okay, so those are what we're going to have to pull off the graph, but we're going to have to calculate some things first. Okay, so if we look at the graph and we look at P to B, okay, we're looking at 34 psi. You're like, well, how do we get that number? Good question. All right, if you look at the bottom of the graph, remember that's our flow in gallons per minute. The example is asking us at 12 gallons per minute. So on the bottom of the graph, if you go over to 12, okay, and then we are looking for P to B, that's going to be the solid line. So you're going to, on the bottom of the graph, take your finger, go over to 12, and then drag it up roughly to where it meets the solid line. Okay, you'll see that it is roughly 34 psi. Now remember, this is an estimate for you. You can clearly see that it's above 30, right? Because this, on the left-hand side, the psi is going by tens, right? It's going 0, 10, 20, 30, 40, 50, so on and so forth. So the 34 is just an estimate for me. But if I'm looking at 12 gallons per minute, I'm dragging it up, right? I'm not quite halfway to 40, all right, between 30 and 40. So I'm just going to go with 34 there. So it's really just an estimate, okay? So the next one we have to calculate, so what we've been doing, find the areas, okay? And then we want to find the return flow. So we have to calculate the return flow, right? Because we need that for retracting, and that's going to help us find the A to T piece. A to T is the return flow. Anytime we're going back to T, the tank, that's the return flow. So in this case, we're going to use the dashed line. So now that we've got that calculated, we have 15.12 gallons per minute. So take your finger on the bottom of the graph, go over to where 15 is, obviously between 14 and 16, and then you're going to take it up to the appropriate line, which is A to T, which is the dotted line, or the dashed line, not dotted, dashed line, okay? So if we do that, it's going to be approximately 78 psi. So take your finger to 15 gallons per minute, and then bring it all the way up to that dashed line. Okay, it's not quite at 80 when we get there, so we can estimate that it's roughly about 78 psi when we do that problem. So, all right, guys, well, this is the end of Chapter 6. As usual, email me with any questions, else write them down and ask when you get to class. Anyhow, have a great day. I'll see you in class for lab.